Good morning, ladies and gentlemen. My name is Ayush Bhambhani. I am the technical account manager on Ancestry's AWS account team. And it's my pleasure to be here today to introduce our guest speakers from Ancestry. For those who may not be familiar, Ancestry is a global leader in family history and consumer genomics. They harness the power of family trees, historical records, and DNA to help people uncover more about their personal stories and also discover more about their ancestry. So, with a growing network of over 3 million subscriber data, 40 billion historical records, over 140 million family trees that have several billion human nodes, and also the world's largest consumer DNA data set with 27 million plus samples, Ancestry has become a go-to destination for those looking to embark on a journey of self-discovery. Now, as you may imagine, managing and deriving insights from a data set of this petabyte scale magnitude presents its own set of special challenges. But rather than shying away, Ancestry has embraced the opportunity and have found innovative solutions to leverage the latest AWS technologies to power the data ecosystem. So I'm now happy to hand things over to our first guest speaker from Ancestry. She's Ramya, who is the senior software engineering manager at Ancestry. And she will dive deep into how Ancestry is leveraging Apache Iceberg on Amazon EMR to optimize the management and updates of their hinge table, which is over 100 billion rows long. So please join me in welcoming Ramya.
Thanks, Ayush. Are you seeing my right screen, like the
Yes.
presentation screen? Okay, okay. Hey, thanks, Ayush. And yes, at Ancestry, at Ancestry's EDM, we have lots and lots of data, right? Subscriptions data, orders data of millions of our customers, DNA activation and fulfillment data, trees data of millions of trees, person and hints data of billions of Ancestry profiles. And our prior infrastructure of our EDM looked like this. We had almost a petabyte of data in our data warehouse, which is Amazon Redshift, data from several different sources from across different teams within Ancestry, and third-party sources from Kafka, APIs, several databases like MySQL, Aurora, MS SQL, files in S3 bucket, SFTP, they all got ingested directly to Redshift staging tables. And from there, different ETL processes would dedupe, read and write data into several intermediate milestone and report tables, right? From the report tables, several organizations like finance, analytics, product, they would all query and produce several metrics and dashboards. As you can all see, various resources writing and querying to and from Redshift, we had severe resource constraints on Redshift, which led to its performance issues. The same query would take 10 minutes or 1 hour, depending on the time of the day. We tried alleviating this by assigning different queues to different user groups, which manage the concurrency and memory available for each of those user groups. We also monitored and optimized the Redshift cluster itself and also the queries that ran. Also, we had complex ETLs that orchestrated the whole flow of data across various stages, and it had validations where a single missing data could cause blocking pipeline failures, even if it's unrelated, resulting in frequent data delays. Also, not all critical tables have evolved to the business model, and all these, as you could guess, cause data engineers and developers to spend long time debugging and chasing data issues. We knew we had to re-architect, and we were given clear direction to move ingestion and some of the data processing to the data lake. We will discuss today about daily picks, the use case that started our data lake evolution. Daily Picks was conceptualized as a ML-driven approach to rank recommendations, aiming to boost hints engagement. This would enable us to send more meaningful recommendations via email, thereby increasing our customer engagement. This was our primary use case, and our proof of concept was to test this around 2 million Ancestry users. On Ancestry, hints are one of our powerful tools to help users make discoveries. They are represented by well-known shaky leaf, and they are based on matching historical records like census, birth or death certificates, or even photos and documents from other trees. Hints fuel user engagement and are a starting point of Ancestry's flywheel. Users explore the leaves, make discoveries, and keep coming back to find more. So our first step towards building daily picks was to ingest the hints and tree data into the lake rather than allowing the machine learning models to query it directly from the Redshift. This shift helped us lay a strong foundation for our data lake and for future modernization efforts. So the project comprised of 3 components. First involved gathering all necessary data and ingesting to data lake. Second focused on processing the data and composing it into a future set, which would then be sent to a ML model, which produced the most engaging daily recommendations or daily picks for users. Finally, the third step addressed how to serve this to the customers. For this presentation, we will just cover the step 1, the data acquisition process for our data lake, including the challenges we encountered, the optimizations we implemented, and the resulting improvements in performance and cost efficiency. Let's understand the data. The scale and velocity of our hint system is enormous. We are managing several tens of billions of hints, and user interactions are highly dynamic. Hints can be accepted and then rejected within seconds. Many large family trees have hundreds of thousands or even up to million hints in a single tree. What's even more interesting is the temporal spread of data. While most hints are created within the past year, occasionally we see updates on hints that got created several years ago, showing the long tail of user activity. Our tree data includes tens of billion person nodes, and we process millions of hints and person node changes per hour. Our goal was to rank hints across a user's entire tree, not just one individual, but across all the nodes in the tree. To support this, we needed the ability to query every hint, regardless of the status, pending, accepted, or rejected. The hints and trees dataset are distributed across several dozen shards and are deeply normalized, requiring many joins to construct the full hint view. The cost of calling all the underlying services or APIs to achieve this for our use case was just unreasonable. So now let's see how the large and complex feature set was built. So to generate personalized daily picks, we start with the hints, which is several tens of billions of rows. And from there, we join it with the kinship data, which again contains tens of billions of rows to understand the relationships. We also bring in tree data and like how many nodes a tree has, any medias that are added to it. And these are all like hundreds of millions of tree data. And to make the output truly relevant, we narrow things down to specific users in the POC and also their user activity, like what hints they accepted, rejected, reviewed recently. And drilling into all these massive data sets would help us to enable to construct a powerful and personalized feature set. Now that we've covered the complex data sources and how the feature set is built, we'll see how our first evolved version of our data lake. Right? At this stage, Redshift tables got ingested from source data like before. Redshift tables were not updated as frequently as we would like it to, but still to keep things moving, we performed a daily dump of what changed in the past day to the S3 buckets. Using this data, we built the feature sets in EMR, and these process features were then saved back into S3. This became our feature store. For inference, we use SageMaker's batch mode to read the feature store's S3 directory, run predictions through SageMaker model. However, this approach had few key issues. Data was siloed into different dumps, so we didn't always have a complete view. If a new user came in after the last dump, we may have missed generating features for them. Additionally, by the time the model ran, the hint may have already been acted upon, making the inference irrelevant. This setup was a good initial evolution, but clearly had limitations. In phase two, our approach was still similar to phase one, and we continued to get S3 dumps of CDC, capturing all the hints that were added or altered in the past day. However, the key difference here was that we started maintaining our own history of these changes. Instead of just dumping the data, we processed each CDC change and merged it into our data lake table, essentially building the change log over time. This phase also marked our first experiment with the open source version of Delta Lake. Other than the adoption of Delta Lake, the rest of the architecture and process stayed same as phase one. We used this setup until our first POC, where we launched email-based hint recommendations, which led to our increase in hint engagement. The next phase was a major milestone, moving from a limited POC to launching hint recommendation to all users right on the homepage. That's a high visibility surface, so we had to scale things up significantly. To support this, instead of pulling from Redshift, we went directly to the source. Trees data was from the tree database shards. Rather than getting the past day CDC from the Redshift, we queried CDC changes from the source database and dumped them into S3, and then merged it into our existing data lake tables. Hints were easier. There was already a stream of changes published via Kafka, and so we used Kafka Connect and dumped them to S3 and merged those to our data lake table. This phase also marked our first experiment with Apache Iceberg tables, which we've had great success with, and we use till date as a standard for our data lake as a data lake table format. Some of the things we tested for source data ingestion. We explored using DMS, bin logs, and enhanced bin logs, and also Redshift Zero ETL to stream changes directly from the source databases. However, the DBAs strongly advised against them due to concerns about performance impact. Too many readers on the commit log could slow down or affect live database operations, especially for customer-facing systems, which was a hard no. That time, bin logs were disabled and we weren't allowed to tap into that stream. In short, any solution that introduced risk to production databases, especially those critical to user experience, was not an option. We just ended up using a MySQL client to dump the RDS data, and also Kafka Connect to dump the Kafka streams. Thomas Cardenas, who is our staff software engineer, will continue talking about data lake, table design and management, various optimizations we did, and how we benefited from them all. Thank you all for listening to me, and over to you, Thomas.
Yeah, thanks, Ramya. So we'll talk a little bit about the table that we delivered for this. One of the interesting aspects that we hadn't done before was this was a completely singular table for hints. In the source data in Redshift, it was spread across multiple tables. And they only contain data from that source system. If you needed other information, you need to go somewhere else. So for this one, we went with the wide table design, where it's denormalized. There's some duplicate information in here. We pull information from the trees org because the hints and trees are different orgs. So if the tree was deleted, if the person node was deleted, that wasn't reflected in the hints data until now. We did that join for our consumers. And by doing this, we reduced costs by 80%, which saved terabytes of storage. And we also baked in the business logic because our databases, our Aurora databases, all our main data sources are for performance for the user. How can we deliver the data fastest to them, not for how we can report on analytics or any other source of stuff. So the databases can be spread across multiple databases and not be optimized. So we kind of re-optimized it for our clients since that's who we serve. So some of the issues we saw when we made this migration of going from just a few users to every user, which is the updates are all over our partitions. We had initially partitioned by user status, what type of hint it was, and that was great for clients, but not great for updating. As Rami had mentioned, 75% of the hints that came every hour were happened within the last year, so they were all pretty close to each other. And then you get a couple tens of thousands from 2008 or 2010. And so essentially you had to load up the entire table into memory and do the merge. And so we tried a few repartitioning with this, and we ended up deciding on group on the iceberg function of truncating. This isn't a real column, but once you say organize the data by hint ID and round down to the nearest million, it groups 0 to 1,000,000 in one partition, 1,000,000 in one to 2,000,000 in a partition, and so forth. Um, Depending on your size, you can create thousands of these, but it somewhat sorts the data. And then for if a hint came in from 2008 and there was maybe one of them, we just load up 2008 and say, update that one row, skip 10 years to 2018, update maybe 10,000 rows, and then we skip to today where we're going to update several million in batches. And so that was able to filter out some of the data we need without doing a full table scan. And I post an example of how you can filter that out using the merge statement um, at the bottom. The second issue is now that we're doing these micro batches, we're not loading up the same data. We're doing hundreds of these micro batches. It took hours to do a single hour. And that's because by default, when you do a merge in Iceberg, it's copy on write. So any file that gets touched gets completely rewritten. And that is great for client reads, but it's costly and it's slow for updates. So reading the docs, we were going through, we found out merge on read, we tested it out, dropped it from several hours to just 15 minutes to do hundreds of updates. And like I said, CPU cost and memory cost went down in the 90% range. So it made the project feasible, else it was going to be very expensive. And as long as you compact on merge on read, you don't have to worry. If you go days, hours, depending on your volume, readers can get really slow, really slow. So the next part is doing just that, compacting. Okay, we say we need to compact because that's what you have to do when you do merge on read. It had the same problem, take hours to rewrite because if we're rewriting several partitions and one partition is really hot because it's the last year, things get updated frequently. Well, looking at the docs, they weren't very accessible at the time because we did Iceberg pretty early on. The current compaction, um, it would do one partition at a time, one file group, um, which is very slow. So we, once we learned that, looking through the source code, we update the 2025, that increased things. We also had to determine what compaction strategy they have. They have three: Z order, fully sorted, or bin pack. Our data was fully sorted or semi-sorted already with the hint ID, and the other one was that row is probably going to get rewritten in another hour or so. So let's just compact it as fast as we can, and we'll worry about that. And then because we had thousands of partitions. If it got to the very last one and where the partition was really hot, there was a lot of files that need to be written, and it failed because it ran out of memory, we would have to restart all the way from the beginning. But there's a feature that we have to enable, partial progress enable, which every so often it would commit. And so we didn't have to roll back to the beginning. We could save some time. Now with this, if it does fail, you have to run the remove orphan files, or else your S3 costs can go up. So you need to go make sure that, hey, if a commit failed, we need to go clean that up every once a week, whatever your cadence is. And then with deletes, delete files for merge on read, you have to enable rewrite all, or else it'll just compact the delete files and you're not really rewriting that file entirely to where you don't have to apply the delete files. Now that worked for a year or two, and then we moved on to some more features, such as Iceberg enabled storage partition joins. So by default, when you do join two data sets in Spark, Spark assumes that the data is not sorted. So it has to sort it and then do the join, which moving data across nodes is expensive. But with storage partition join, if you're joining two Iceberg tables that are partitioned the same and they use the join key to partition, Spark's like, I don't need to sort. So I save compute. So that's like, well, if that's the case, let's just make all our temp tables Iceberg. So don't use Parquet files, don't use JSON files or anything, just use all Iceberg, and you can just enable this, and hopefully you can use it if you set up your table right. Table schemas, um, our data warehouse was completely flat columns. So if you had 6 columns that were all related, you might have really long names or ambiguous names, and you don't know how they relate. So to make things easier, we started using Spark's structs to be able to group like columns together. And that made looking at the data, understanding the data better, especially since we were denormalizing the data and had some duplicate columns. It just made reading the data a lot easier. So today's landscape, every data set's Iceberg. We had the best performance and usage of Iceberg, so it won. EMR compute, that's how you build tables, that's how you alter tables, update, and we can create several clusters. We don't have to have one Redshift cluster, we have several EMR clusters that don't have to impact each other. One thing we didn't talk about, but Ramya mentioned, was if there's a row missing, it blocks everything. The source tables, like the hints table, like this is the definitive table for hints, it's eventual consistency. So we're pulling data from all these different data sources. One row might get there before the other, and it's on the clients to determine how they count it. Do you count this row, or do you wait for the other data to arrive and then do you count it? That's on them. That's really enabled us to be non-blocking, as well as that schema, that denormalized schema, doesn't match the source system because they're highly normalized. And so whenever they make migrations, only one team is impacted. Not all the reports are impacted. Not all the ETLs are impacted, just a small section. And we went through a number of migrations and we felt that, that, oh, we make this change and then a lot of our reports are affected. So it did make it easier doing that. And so this is kind of what it looks like. One team manages the ingestion, and then that goes to where they imply that business logic. And then that table is the one that gets provided to data scientists, other data engineers, or who else needs that data. So thank you. That is about our project, Daily Picks. And
Yeah, thanks, Thomas. Thanks, Ramya, for taking the time to put all of this together and presenting today. So I'll now hand it over to our host, Sridhar.
Okay, I'm opening the floor for any questions from the audience here. I'll start off. Ramya, you started the use case with the ML-based ranking of recommendations with increased engagements there. This is a two-part question. How long did this journey take to go from when you said evolution? Was it over years or over few months? And how did it manifest itself? Were you able to, at least from a business impact perspective, did you increase the
Mhm.
hint engagement from the
Ye-
customers?
Yeah. So we increased hints engagement by 6%, even in the POC. It doesn't matter if the all hints would be accepted or rejected, right? As long as the user would act on the hint, it means that they're interacting more with us. And even in the POC, we saw a 6% increase. And yeah, it took months, not years, but maybe over a year, Thomas, like for all the phases and to be fully done. Is that fair?
Yeah, to get Daily Picks launched, that was within 6 months. We went to the homepage a few months after. And then it was mostly the first probably years getting all the data, like figuring out what data we need to pull into the data lake first, and slowly replace the uh, the uh, the Redshift uploads to use that data source from the data lake. That took the largest portion, and then I mean, just the last 2 years, we were focusing on the subscription data, which took 2 years to kind of make that transition.
And also several teams were involved, right? Like, so the step one, step two, step three, like they're taken care by several teams. So there is also that parallelization. And so it's not like you did each of those, one team did each of those process and then we released it. So that helped as well. So yeah, our data science team and
See, considering the nature of the data, uh, how did you address the security and privacy while you were architecting these? Were there partners from the security team or application security or the data security or compliance there? How did you navigate that?
Yeah,
so
or Ramya.
no, so like for all, so I'll give my shot and then Thomas can answer too. So all of our data, right? Like this project has nothing specific to security than all the other databases and everything we own, right? Like we've been with AWS since 2017 and we have so much data, lots of RDS and I mean, DynamoDB, all kinds of databases. We have DBAs, and then we have our InfoSec team. We also have our policies and everything in place, right? Like we cannot you cannot do things that the cloud ops doesn't want us to. It's all restricted, and we just create access control policies and other things for what we can do, and we do things. But the AWS environment itself is already we have all kinds of resource-based, access-based, all the policies and everything in place. And we know how to handle PII data, like DNA data, for example, is very sensitive. We have things in place already in data warehouse, right? Like how to handle PII data, what to do when there is a GDPR delete. So those are all in there already baked. And so that is something that I just wanted to explain about already existing things that we that just works in our favor. And Thomas, you can add to it.
Yeah, I mean, security and data privacy is a big thing at Ancestry to making sure we protect everything. And so we always have the experts on hand to be able to go talk to and get that early feedback with, and just how we structure the accounts or the bucket policies, um, cross account access, stuff like that. So user groups that like, is this person even allowed to view this data, stuff like that. So yeah, they helped out quite a bit with it. So.
Yeah, and then just to add to what Ramya and Thomas said, so Ancestry's other teams as Ancestry, especially the InfoSec team, has been in touch with us throughout. So they take a lot of time to go through SIP sessions, well architected reviews. We saw around over 150 people participate in the security activation game days last year. So they have been, very strict about security, and then they work with us all the time trying to understand what the best practices are and make sure that they are aligned as much as possible.
Don't see any raised hands here. Oh, there's a question here. There's a question from Ravi. In the final architecture, was the data stored in S3 and then to Redshift, or were you able to bypass S3?
So yes, all the data is stored in S3. Only data that is built for the report or a dashboard would go to Redshift where our analysts live. Our analysts all go to Redshift to do their to go query data or to um, view a dashboard or have the dashboard connected to it. So the data lived in S3, and then if a person wanted to report, we just copied that specific data they needed to Redshift. So we didn't always copy data to the Redshift. We had more data in it.
So so one thing to add is, so now in today's world of EDM, so the way we do is, though we say them as like S3, the other thing is we call them as iceberg tables too, right? So those are our data lake tables. So the way we think is any data, so instead of just ingesting to Redshift, it's like we get them, like we have a raw, refined and processed layers within data lake, right? Like which are our iceberg tables. So that is our new norm. So it's kind of like, hey, get the data, dedupe, and do anything, even a lot of business logic that is needed, and have them as like, though they are essentially like Parquet or some files in S3 bucket, we have that iceberg table format on top so that we look at it as a iceberg table, which is our data lake table. And then from there, we take things like from data lake to data warehouse as needed. And then from there, as Thomas mentioned, to different, there are some dashboards which we even served from data lake, but not all. Lot of very important SLT and important dashboards, they go from Redshift. But even then, it's like not a giant ETL that would do everything from ingestion to dedoping to everything up to report all in one. But it's like, think of like micro ETLs where like an ETL would just do ingestion and and then like get things prepared and nice in data lake tables, and then from there the last step is to copy to Redshift as needed.
Yeah, and I'll also add, we also gained clients because before EDM was mostly FP&A product analyst. That's who we support. Now we're able to support DNA science because they can query the data like they use Spark. They don't use Redshift because before they would just have to go dump from Redshift and then read it in. Same with our ML team, other ML teams. They would have to dump stuff from Redshift to go query it. When we had some people access us with Athena for more client-facing activity. So it really added clients to us when we moved to the data lake, able to support more people than just FP&A and product analysts.
Did you collect, is there anecdotal evidence that this improved their workflows for your clients there in terms of whether it is performance or accessibility to the data itself?
It overall gave, I mean, the whole thing, right? And again, it's an emerging thing, right? As we are adopting to this and we are moving to this, I feel like it has changed the overall PR of EDM or like the organization itself, right? So it's more like, not like, hey, we have one way, like this is Redshift, you have to do queries from this, and that has changed to, yeah, oh, are you using Spark? Like, there is different things, right? Like you can do, like last year, like for Turkey is big, like Thanksgiving sales and stuff. I know like Thomas and team, they were able to uh, um, bring up like T5 dashboards, like directly from data lake in like a very short period of time. Like we are seeing, like, for example, oh, marketing, do you need this? Sure. Like we are able to bypass several layers and just deliver quickly what is needed. And that is like a new new facelift, like even for the organization, and how we are able to deliver things like much sooner. Yeah, that's my take.
How's
Serve
the
more
future
clients.
looking? What additional things are you looking to? I know that you said this is an evolution there. what would be your North Star? When do you feel that you've achieved what you're looking for?
So we have an awesome director who keeps giving us direction. And so I know for now we are even thinking in terms of, I mean, he can speak the best for all of this, but I know that like we are even, there is lots of work from the sister teams in like making separate Redshift clusters, right? Like on like, instead of having one giant cluster, like as things needed when there are need for Redshift, like make them smaller and smaller, and then more and more on data lake, right? Like anything we are like, even as we speak, like lots of tables we are redesigning where even like in Redshift, our dim table and facts table, right? Like the dim tables, even them, we have started having some dim tables in data lake. Now we'll be doing more and more, right? Like instead it's almost making trying to, I mean, Redshift costs a lot of money to so like making Redshift thin and as needed and spinning separate clusters, and then also making a data lake and processing in there more and more. So that's coming, and even dim table, that's a new thing for us. Okay, even move dim tables. Like why take it all the way to Redshift? Why wait till Redshift? Have them here, have static tables or slow changing dimensions right here in data lake, and then like moving to Redshift is just like one step. It's like just do it so that it's like, you know, nice to like the other organizations. Some organizations are used to showing dashboards connecting to Redshift just for them, right? Yeah. So
And I'll also add, there's another team that we work with that they're working on the observability, so that if there's a report that is having issues, we're able to easily track that back to the source. It's like, oh, this eventual consistency model, there's a lot of inconsistency happening in that source table that we mentioned and stuff like that, especially when we start to grow to, more hundreds of tables. And things like that, being able to track the costs more, with individual pipelines, and yeah, just how do we create those tables faster and allow people to experiment and create those tables with maybe not being data engineers being involved. So yeah.
two things I want to add are like audit platform. Yes, that's a big thing there, because when there is a problem, how can we know faster? And also the other two things are lineage, like working more on lineage. So how soon can we just know when something is, because the problem with data is it's like when if something is broken for customers, it's easy, right? Something gets broken, immediately there is this, like everybody knows that it's broken. But deep down in the data realm, it's like it's all we are taking customer data across several tables, right, to various reports. And if something gets stuck somewhere, how soon to detect it and like where the issue is, right? And that's why modernization and also knowing lineage, how can we find several operational dashboards even on data, even on the data ingestion side and the ETLs. And yeah. Um, that-
That's good that you read our mind as to, I was curious about the observability portion there. So it looks like that's something in progress and you're going through that journey there. It was a great insight.